Welcome to Physical Chemistry. This year, I thought I would go about this from the high energy side. So we will look at the nuclei first, I think, because that's where our highest energy possible interaction will happen. So in a particularly unusual type of spectroscopy, we can imagine that we've got some iron, and the iron is iron nuclei. Sorry, it's a little bit out of focus. We've got our iron nuclei, and the iron nuclei will emit occasionally some kind of radiation. If it's a gamma radiation, so it's a gamma. If it's gamma radiation, it's effectively a piece of electromagnetic energy, a photon of electromagnetic energy, and it's coming out of the iron nucleus. And in this case, what we're interested in is a type of radiation that comes out. So that obviously the gamma radiation is coming out and nothing is changing. There are no differences in the sub-nuclear particles, so that's the neutrons and protons. So something must be happening to just the energy, and that energy must be stored in our nucleus in some kind of form. Typically, there would have been a decay of some kind, an alpha or a beta decay, so an actual nuclear decay, and the iron would have been oscillating in some way. This nucleus would have had some kind of kinetic energy. It will have been vibrating, and that gamma radiation will be a step down in vibrational levels of our iron nucleus. If we have another iron atom, Fe, nearby, it can absorb this photon. It can also be slightly affected by what the electrons around it are up to. So if we take some iron, 56, and we expose it to radiation, then it becomes radioactive. It will give out these gamma rays, and we can capture them with another piece of iron that is next door. Nothing is interesting about that just yet. Well, it is interesting because we know that these have the same fundamental frequency. They've got the same kind of energy levels inside them. But what if we then alter the energy levels of this iron slightly by binding it with something else? So we make iron oxide or something. We have a different type of iron. Then it won't be quite the same energy level, and this this gamma radiation will tend to pass straight through instead of being absorbed by this nucleus. So we will have a lower absorbance, we'll have a lower ability to absorb this radiation if we change the chemical state of this iron. It's not very much because the nucleus isn't affected very much by the electrons, but it will have an effect. Then we come to the clever bit. So now we've got radiation that's coming out of this iron and radiation that's being absorbed by that. So we've got one color is coming out effectively. This is just one color of radiation, and we would like to change the color. So what we need to do that is to take our piece of iron and move it at a different velocity towards or away from this other piece. And then we can Doppler shift. We can change the frequency of this gamma radiation, and we can use that effectively to scan with a physical mechanism. We can accelerate this piece of iron towards the other one, and then stop it, and then accelerate it away, so effectively it's bouncing up and down, and we can use that to probe this other piece of iron to see what its relative energy level is, and we're looking at the gamma radiation that's coming out of the nuclei. This type of spectroscopy is called Mössbauer spectroscopy, obviously after somebody's name. Sorry about the weird shiny bit. It keeps changing. The significance isn't great because we would need a radioactive source. It's very fiddly. It only works if we've got a radioactive source of the same element that we're interested in. It's somewhat difficult to do because we need to have it going quite fast to be able to change its frequency reasonably. And then obviously it's going to crash into our sample fairly quickly, so we've got to do something about that. Typically we would rotate it or accelerate it linearly against the spring so that we can measure. We need to know what the speed is. We need to know what we're looking for. And we also need to measure the radiation that comes through. But mostly the problem is we have a radioactive source and we have to deal with that. We need shielding. It's not very practical. But from a teaching perspective or from an interest perspective, it is quite important because we can use this Doppler effect, accelerating the ion towards and away from the other piece of ion. We can use the Doppler effect to shift the frequency that this other ion nucleus sees, and that will determine whether it can absorb it or not. So moving a little bit further out, we've got our electrons of the ion. Some of these electrons on the outside will be doing bonding with either metallic bonding with other ion atoms or other types of bonding with other atoms. But the highest energy to be got, the highest energy place, would be this internal 1s electron, which we could shoot all the way out into, to make it free, all of the way out to the environment. So we could do that. And we can do that with a photon. So let's do that. And this photon would be X-ray photon. So this is H nu. So we've gone from gamma radiation to X-rays. There's no real fundamental difference between them. This is a fairly high energy X-ray, but it's not super high energy. The interesting difference is that instead of talking to the nucleus, we're talking to electrons. So there's just a slight energy difference. The highest energy, as we say, is to be got by falling into this energy state, to the lowest energy state, or the highest energy we can put into our atom, into electrons, would be to knock this one fully out. We can give it as much energy as we like in kinetic energy, so that bit is free, and we can think about what our requirements are. So the reason that the last type of spectroscopy worked is that the ion nucleus was oscillating and it can only absorb certain energies. Now we've got an electron which can also only absorb certain energies, but it can absorb more than that because it can carry on straight. And we also would like a reasoning for why this photon couldn't, or the last photon, the most power photon, couldn't excite the nucleus and excite one of the electrons at the same time. So we need a time constraint. When this light comes in, the photon comes in, and an atom absorbs it, it doesn't have very long to deal with the energy. It has to go somewhere immediately. And what that means is there has to be somewhere for it to go. So we can't divide this energy into nuclear energy and electron energy. We can't divide it between this electron and this other electron. It has to go into one immediately, and then it can be distributed. So the atom has to be able to absorb this energy into some kind of energy level. In this case, it's not an energy level because it's gone out, so it's actually free. So there's a near continuum. The speed of the electron is quantized, but the quantum levels are very, very close together, so we can't really say that we can see them very easily, not certainly compared to the difference in energy between here and escaping. So we can imagine that there's a problem with our spectroscopy that we're going to use, and that is that if an atom absorbs a photon, it has to do something with it very quickly. So there has to be an energy level where the photon can go, otherwise it can't absorb it. This is good because it allows spectroscopy to work, because if we have an energy level for it to go into, like those iron nuclei, if there is an energy level for it to go to, it can be absorbed. If there isn't, then it can't be absorbed. If it's close, then it can be absorbed a little bit. If it's not very close, then it can't be absorbed at all. And so we can get some kind of effect. Quantum mechanically, we would imagine it would be absorbed or wouldn't be absorbed, so there would be an extreme effect, 1 or 0. We will discuss at a later time why that isn't always the case. So if we have our energy along here of our photon coming in and the relative intensity, so if we take this blue line, we can have lower energy. It's not enough to kick this electron out, so it can't be absorbed. And then any energy more than that can be absorbed and converted into kinetic energy. It's a simplified version, obviously. On the other hand, we would measure these electrons coming out, for example, and we would get no electrons out, and then suddenly we get a jump when we've got enough energy of our photon to kick it out. So we can use this as a type of spectroscopy, but there is an easier way. It turns out that getting a varied frequency X-ray source is difficult. It's technically challenging, but it is comparatively easy to have a single color X-ray source. And if we have a single color X-ray source, then we can do different interesting things here. So if we take a single color X-ray, which is enough to kick this electron out, we would see exactly the same thing, but the other way around. So if we would see no electrons that have more energy than our photon coming in, because that's impossible. We would see no electrons that have more energy than the sum of the energy of our photon minus the energy of the electron orbital. Or as soon as we get below that, we see a lot, and then it goes up a little bit more, and then it will decay afterwards. And typically, for this type of spectroscopy, we would flip that axis and model it, or call it binding energy, the amount of energy binding this electron into our orbital. So here we are, we've got our diagram flipped, we've got our graph flipped. This is a type of spectroscopy called X-ray photoelectron spectroscopy. Photoelectron spectroscopy. We're measuring the energy, the kinetic energy of the electrons coming out, and we're putting in a photon of light, and the photon of light has to be relatively fixed in energy. So we need a single color source of photons. They will knock out electrons from different orbitals, and so we will see a variety of these peaks. I've only drawn one because we're only thinking of one right now. This is the one simple form of this spectroscopy. The interesting thing about this type of spectroscopy is just like the Mossbauer spectroscopy, but much, much more so. If we connect our iron to oxygen, for example, it will shift the energy level of this orbital, and we can see this in the energy of this peak. The binding energy of the electron is dependent on how much shielding there is effectively from the other electrons. So if we connect this iron to something like fluorine or oxygen, it will pull electron density away from the outside, which will mean that this electron is better bound to the iron because there's less negative charge outside. If we give it electron density by connecting it to something that will donate electrons in, so organic things, for example, we will have more electron density outside, which will mean it's easier to pull this electron out because the whole atom as a whole is more negative. And then we can remove this electron, so we will shift the energy down, which is this way. Once this electron has been kicked out, then there's going to be a gap here. Oops, let's rub out this X-ray. There's going to be a gap here where there used to be an electron, and our nucleus will be positively charged. Wrong pen. Here we go. So we'll have a net single positive charge because we're missing an electron, but we've got a gap right down in the bottom. So this electron, for example, or one of the others, but this one isn't involved in bonding. So this can drop down here, and that will give out some light, a photon of light. This is also an X-ray. It's got slightly less energy than the previous one, because it's the difference in energy between the two electron levels. And it has some important characteristics for us. The first important characteristic is because the energy of this X-ray is dependent on the energy of these two energy levels, then it is less affected by bonding than the energy of a single level, because you can imagine they move up and down together. So the difference between them is comparatively unaffected. It is slightly affected, but it's not very affected at all. That is good and bad for us as material scientists, because we would like to know what element this is, and it's a lot easier to determine what element this is if the energy of the signal that we get out is always the same. So it is easier to determine the element, but it's harder to impossible to determine what it's connected to. So if we have a mixture of things, or we have a chemical molecule, we can't necessarily tell the difference, but we can say what's in there. This is particularly good if we have a sample and we don't know what's in there at all. We will first of all want to know what elements are in there. The other good thing about it, or the other important thing about it, there are two actually, but one of the other important things about it is that the energy that came in is now irrelevant, because we're only talking about the energy between the hole, where the electron used to be, and where the electron is now. That is all that has to come out. When this electron drops down, the atom has the same problem as it had when it had a photon come in. It must get rid of that energy very quickly, so it dumps it, in this case, into a photon and just loses it. So that means that if we have a source of energy that is not as unique, is not as single-colored, is not as monochromatic as we had before, we can still do this type of measurement. That's why this is useful inside an electron microscope. It has two advantages in the electron microscope. One, there are electrons everywhere anyway, so it's hard to measure, hard to find the correct type of electrons that we're looking for, because there are all kinds of types of electrons in there, including the ones that we put in, but also because the energy of the electron coming in is less defined than the energy of a photon, and when our electron comes in and it knocks this one out, for example, if we shoot an electron in, it knocks this internal electron out, then the excess energy that we have is spread between those two electrons. That makes it harder, but not impossible, to tell anything about our atom from the energy of those two electrons. It's not entirely impossible. There is a method for doing it, but what we're interested in here is an easier way, where we measure this X-ray photon that comes out, and it is not affected by the not monochromatic nature of the incoming electron. It is also unaffected by the charge on our atom, where the electron was slowed down by the positive charge on the atom, and if we try to then knock a second one out, it will be slowed down more by the positive charge. This photon is not affected. That's good in electron microscopy, because it means that we don't have to ground our sample if we want to measure this photon. We do have to do it if we want to measure a good electron microscope picture, but for measuring the element, for analyzing the elements with this, which would be called EDX, so it's electron dispersive X-ray analysis, because the electron is coming in and we're measuring the X-rays. The X part comes from actually the method of measuring the energy of this X-ray. That's less important right now, because we're interested in the moment, at the moment, in exactly where it comes from, because I'm more interested today about what happens to our atom. So at this point, we can measure the energy of this photon, and we can tell which element it came from. Some elements have similar energies and they overlap, and so it's difficult, but for the most part, that's how the technique works. That isn't the only thing that can happen to this energy. So there is a weird thing that can happen here, that instead of losing a photon, this atom can do something else. It can kick this electron out. So this is E minus, and it's got some kinetic energy. We can also measure the energy of that electron. This is called Oge Spectroscopy, from the person's name, and it is an alternative. So we put in energy, we knock out this core electron, a second electron drops in, and the third electron, which is this one in this case, gets ejected for the same reason, that the atom is stuck with this quantum mechanical problem. It has so much energy, and it's got to do something with it immediately. If it happens to be able to eject an electron, it will do so instead of giving out a photon. It turns out that light elements are more likely to give out, which way around is it? Light elements are more likely to give out electrons, and heavy elements are more likely to give out photons, which means that if we're measuring the photons, the X-rays, it is a bit harder to measure light elements. There's another problem, obviously. If we get down to very light elements, we're talking here of a 3-electron process. We're knocking out an electron, another one falls into the hole, and a third electron is kicked out. So obviously our atom has to have 2 shells, and it has to have 2 electrons at least in the second shell, and those have to not be bonding electrons, so really we have to have 3 shells. That knocks out most of the lower, lighter elements as good candidates for this type of spectroscopy. The X-ray measurement is a little bit easier because we only got 2 electrons in 2 different shells taking part, but it's still not very effective for light elements. Our particular machine, the one in our electron microscope, will measure boron, but it struggles. The sensitivity for boron is very low, but it can measure it. That is about the limit. The main problem with this is obviously hydrogen, because hydrogen is quite common and hydrogen is completely invisible. It's only got 1 electron. It can't be seen by really any of these techniques. We can only detect it as a shift in X-ray photoelectron spectroscopy. So now we have a process inside our electron microscope for measuring elements, for detecting elements at least. We have an electron coming in, it knocks out another electron, so we get 2 electrons out, and a third electron drops into the hole, giving out a photon, with the difference in energy between these 2 energy levels, whatever they are. This is how monochromatic X-rays are made, which was what we were using in the XPS. So we need to be able to do that. So what we need is a metal, typically, or it's a lot easier if it's a metal because we can get rid of any charge that builds up. We accelerate electrons into it and they whack into here, knocking out another electron. There is a problem with metals though. When the electron goes through the conduction band, it's effectively breaking the laws of physics. It goes from a high speed, whatever speed it is in the vacuum, into the metal. It's actually going faster than it should really be inside the metal, and so it slows down, giving out energy. So it's going faster than the speed of light, or it would be if it carried on. So it slows down in the metal, and that causes it to give out a lot of X-rays. Those are relatively broadband X-rays. Those are the ones used in X-ray photography, for example. And it's also if we want to measure other things, so if we want to measure broadband X-ray measurement. But what we actually want here is this one, which will appear as a spike in energy on a background of the normal X-rays of the Bremsstrahlung, as they're called, the slowing down electrons. Bremsen is braking in German. It's obviously discovered in Germany. It's a type of X-ray generated when an electron slows down to the speed it's supposed to be going inside a metal. If we want these ones, then we need to block the other ones in some way. We need to reduce that, but we'll cover that when we're covering how to make light the same color in other types of spectroscopy, because we have the same problem in those too. So this is what we would see. This is a place that I've stolen it from, what we're looking at. So it's group, and it's their web page. What I want to show you on here, I'm trying to work out where I'm looking. What I want to show you on here is this peak, which is the silicon peak. So we've got the silicon 0, which, as they show, is some silicon and a silicon wafer. We've got the silicon 4+, which is SiO2 typically on the surface where it's oxidized. And in between, we've got silicon of other types, and that will form this broad band in between. So what we really see is if we go deep, this is ablation, it means they've shot some off the surface. So if we shoot off 3 nanometers, we get just silicon 0, You're obviously in a vacuum. If we start on the surface, we get just this black peak, which is this, and we see into the surface, so we see some silicon 0, so it's obviously very thin. And if we, here it is. And if we go further in, this peak goes down, and this shoulder region, the intermediate region, goes up, and it sort of flattens. So here we go. It shifts in, which means that there are stages in between the 4 and the 0. There's some kind of silicon suboxide between. That is what they're trying to show here. If we go to, let's have EDX next. So this is where I've got it from, so that you can see it's this place. It's a Wikipedia image. Here is what a typical EDX or EDX would look like. So in this case, we're shooting electrons in, we're getting X-rays out. We can see these lines. So this would be a line for iron. It's not the only iron, so there's a K alpha and a K beta. K comes from the K shell, which is the inside shell of iron. It's the first one. L is the next shell out, and M is the one further out. We can see, so we've got 2 peaks from iron. Calcium has got 1. Silicon has got just the 1. Oxygen is right down low, and carbon is even lower. The heights of these peaks is not, well, it is compared to the amount of elements that we see, but there is a factor for each of them, because the heavier elements are much more likely to give out X-rays than the lighter ones, and so therefore we've got to alter it. That's why the carbon is so low. Typically on nearly every surface there's a lot of carbon, but the intensity of the band is very low because it's a light element. It's hard to hit with our electrons, and it doesn't give out X-rays very efficiently, whereas the iron gives out plenty of X-rays. We can see it in the iron. Whoops, there's another one down here for a different transition. Don't know where it's going. Right. If we get on to Oge, where is it? Oge. Lost it now. Yeah, that is where I wanted it. Here's an Oge. So this is where I got it from cnx.org. And we can see in the normal spectrum, which is the red one here, we can see we've got little tiny peaks for each of the elements, because we see typically a peak for an element, or several peaks for an element, just like in the X-ray analysis. But in this case, they're subject to a slightly different physics. So the spread between the heavy elements and the light elements is different. And this is a trick that one often uses. You may have used it before. What we can do is we can take the derivative of the spectrum, so that's why it says DNE-DE. It's the derivative of this red spectrum, which helps us to find the top more easily, because you would expect that to be a sharp. So you'd expect it to be a sharp line that goes through 0. 0 is the maximum. You'll have done that in maths. That's how you find the maxima and minima of a curve in maths. I expect you've done that in maths because my children are doing it in school. So if we do it in a purely graphical form, because we don't have an equation for this line, but we can still draw a derivative because we've got a lot of points under here. We can see here, for example, where it crosses through 0 again is the exact point where the top is. It makes it a lot easier to find the tops of these weirdly shaped peaks. What I wanted was this one, which is very small. This is the X-ray generation to Auger photons. You can get that from all kinds of places, but that's a quick picture of it, showing that the X-rays go up and the Auger electrons go down as the mass of the element goes up.